So here's my setup for the marble down the ramp experiment, where we're going to be investigating the relationship between distance down the ramp and time for a marble to travel. I've got my data table ready and I've set up a ramp. I'm going to measure the height of the ramp, and so getting my head down close as I can to the measurement so I'm in line with it, and taking into account there's a little bit at the end of the meter stick, a few millimeters, so I'm going to take that off my measurement. So my ramp height is about 0.122 meters, or 12 centimeters and 2 millimeters, or 122 millimeters. I'm going to record that on my table. Let ramp height equals 0.122 meters at one end, and so if anything gets moved or adjusted, I can set it back up to the appropriate height at one end. And I'm going to start off nice and low. I might try 5 centimeters, and when I start and stop, I realize that the times are so short it's really hard for me to actually stop the timer accurately. So I'm going to start at maybe 10 centimeters. Okay. So that was 0.59, 0.53, 0.53. I'll go one more time. 0.53. Come over here for my distance of 0.1. My times were 0.53. I think I had 3 times. And I had one 0.59. And they're all, reasonably close together, so I'm happy there's no major outliers there. And then I'm going to do my next height, or my next distance, sorry. And so for my next distance, I'll go to 20 centimeters, or 0.2 meters. 0.75, 0.75, wow, 0.75. I'll do a fourth one, 0.78. So back over to the table, 0.2, 0.75, 0.75, 0.75, 0.78. Doing 4 times makes it really easy to spot an outlier, and then to give me a good number of, if I do identify an outlier and remove it, then we'll have a good number of times to work an average out from. So now I'm going to continue doing my times all the way up to a meter, fill in this data table. Okay, so I've got my results here. For a few of them, I've got an extra time. So like this last one, I thought there was just a bit of variation between the 1.82 and the 1.72. So I measured an extra one just to try and give me some clarity there. And I think with these ones, I wouldn't identify any outlier. I'd just average all 5. And up at the 0.8 distance, you can see I've taken a few extra measurements. That was because I felt there was quite a big jump between the 0.8 times and the 0.9 times. And so I wanted to make sure that I was correct there. So when I went back, I got 2 higher results, 1.56, 1.56, 1.50. And so I think I'll just average all of those because they're all very close together. So now we're ready to work out our average times. So I'll add another column to the table. And I'll write up here average time, that's measured in seconds. Okay. Okay, so we're ready to move on to our first graph, and looking at the values, the biggest number we're going to need for distance is 1. We've got 10 values there, so we're going to need maybe 10 boxes. We could go along this way because d is the independent variable. It's going to have to go on the horizontal or the x-axis. There's 22 boxes here, so we could do jumps of 2 boxes, so 0, 0.1, 0.2, 0.3. Because the highest time value we need is going to be about 1.77, so we're probably going to round that up to, maybe 1.8 or 2. Knowing that there's 16 boxes on this side of the graph paper, I think what's going to work better is if we turn it this way, we're going to put time, our dependent variable, on this axis, and d, our independent variable, on this axis. So d is going to go up in single boxes, so 0, 0.1, 0.2, 0.3, 0.4, up to 1, which will take us to about here. And then the time is going to go up in jumps of 0.1 seconds, which means that we're going to get up to about 18, which should be somewhere up here. So I'll go ahead and draw that up and then start plotting my points. And as ever, you guys should be doing this in pencil, so it's so much easier and quicker to make changes if there's any mistakes. I'm doing it in pen just because that's a bit more visible on the video. So down here we've got our independent variable, which is distance in meters. We're starting at 0, and we've got 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1.0. We shouldn't need anything beyond that. For our time, so I'll label up the time axis. I'll put a label up here for t in seconds. And I'm not going to write in every 0.1 because it's just going to get messy. So what I'll do instead is I'll jump up to 0.5, and then another 5 boxes will be 1.0, and then another 5 boxes will be 1.5, and then another 5 boxes will take us to 2.0. And so that should give us a full range that we need. Alright, so average time for distance of 0.1 is 0.55. So there's my 0.1 on the distance, and we're going up to 0.55. So I'm going to put a nice clear cross there. 0.2 goes to 0.76, which will be here. 0.3 goes to 0.94, which will be here. 0.5 takes us to, 0.4 takes us to 1.09, which is going to be just there. 0.5 goes to 1.26. So it's 1.1, 1.2, 1.26 is going to be there. 0.6 takes us to 1.33. 0.7 takes us to 1.46. 0.8 takes us to 1.53. So you might be able to see what's starting to happen with the shape already of the points we're plotting. And then we've got 0.9 at 1.64 and 1.0 at 1.77. Okay. Now, what might be really useful here is if we could go back and measure a 0.05 value for the distance and try and record a time in there. But I think what we've got is enough to show the shape is starting to curve like so. That 0.6 looks a little bit low perhaps for the rest of them, so I'm just going to double check that. 0.6 1.33. It's in the right place, but it might be that my times there weren't quite precise. Okay, so that's going to give us a curve in that direction. And so I'll put my, a smooth line of best fit on there. Okay, so referring to the shapes of the graphs, we can see that our graph is definitely not doing this, it's definitely not doing this, it's definitely not doing this. It seems to be this sort of shape here, doesn't it? So we're going to write on our graph that our y-axis, t for time, is proportional to the square root of whatever's on this axis, so d. So we can see the shape of that graph suggests that whatever's on this axis is proportional to the square root of whatever's on this axis. So for us, that is time is proportional to the square root of distance. And we could write that in symbols as t proportional to square root d. All right, and then we're ready to transform our distance values to square root them and then plot our second graph. So this column is now going to be square root of distance, and whatever we do to the unit, we have to do to the, whatever we do to the symbol, the quantity, we have to do to the unit as well. And so that's now measured not in meters, but in square root of meters. So we go through and square root our values. I've got square root 0.1, 0.32, Okay, so now we've got our square root d values. We're going to go ahead and plot our second graph. And looking at the values, again, we're going to need probably the same scale for time, but we are going to need the same scale for time because we haven't changed that. And our d values, conveniently, they start a little bit higher at 0.32, but they still go to 1. And so I think the layout that we had for our original graph will be ideal here. So let's go ahead and try that. So the label this time down here is square root distance, brackets, square root meters. It's really important to include both of those and show that they both have the same transformation. Up here, nothing's changed, so we're still time in seconds. So I'm going to skip writing all of the 0.1, 0.2 down here just for time. I'm going to go 0.5. I'm going to go 1.0. On the time scale, we're going up to 0.5. Then 1.0. 1.5 and 2.0 up at the top. Okay, and now we're plotting these values here. So at distance 0.32, we're going to 0.55. About there. Okay, and looking at that, it does give us a reasonably straight line. And so I'm going to go ahead and draw my line of best fit. Again, you really want to do this stage in pencil. It's quite interesting that these 2 points at the start and end are a little bit higher than the rest. So probably going to emphasize my line through most of these points and perhaps just missing out on the other two. So I think my line will look something like that. Here we go, and I'm going to extend it down here. Alright, so we can actually see that the line almost exactly goes through 0. But I think it cuts through the x-axis just before, so it's probably going to have a y-intercept of maybe negative 0.02, I think, looking at that, but I'll cover that later. Okay, so first off I want to draw a gradient. I want to work out gradient. So I'm looking for 2 points far apart on the line, ideally where they cross grid junctions. So I think quite like this point here. I'm going to circle that one. And let's find a similar one up this end. Yeah, I think that one's probably quite good just there. So I can see that that is at 1 on the x value, and it's going to be 1.73 on the y value. So I could write those down like 1.0, comma 1.73, and for here I've got what's that going to be, 0.26, comma, and it's 0.44 there. So if I draw in some construction lines, we need to work out what the rise and run would be. Oh, now I'm looking at that and I'm thinking, sorry, that should be, where is it? I think that's actually close to 1.74, my mistake. So let's just change that to 1.74. Okay, so the rise is from 1.74 down to 0.44. So 1.74 subtract 0.44 gives us a rise of 1.3, and our run goes from 1.0 subtract 0.26, and so our run is going to be 0.74. So our gradient calculation becomes m, which is the letter we use to represent the gradient, equals rise divided by run, which is 1.3 divided by 0.74. And that comes out, oops, I missed my decimal place there, 1.3 divided by 0.74, and that comes out as 1.7 Now that should really have been 1.30, I think. And so I'll give my answer to, well, so it doesn't really matter at this stage whether I do 2 or 3 significant figures. If I was doing it to 3 significant figures, I'd be giving that as 1.76 due to rounding, or to 2 significant figures, I'd be going 1.8. Okay, so then we need the y-intercept, and we've come down here, and so we always just extend the line right down to where it hits the y-intercept, and I think that is very close to 0, but I'm not gonna count it as 0 because it isn't exactly 0. So I can measure the distance there and compare it to here, and I think that's about 1 small box. And so 1 small box on this scale, you know that each big box is 0.1, and so we can divide that by the number of boxes. There's 5 little boxes, so we divide by 5. That tells us that each little box is 0.02. So our y-intercept, or C as the symbol we use for it, is negative, because the line came down below 0, 0.02. And we might end up talking about that in our discussion, that is so close to 0 as probably being 0, but we're going to include it in our equation anyway. Alright, so at the next stage we take our equation of a straight line, which is y equals mx plus c. I'm deliberately, well, do I want to write it down? Okay, I will write it down, but you've got to be really careful not to leave y and x in your equation. So y equals mx plus c, so hopefully you can see where everything fits in. Our y quantity is t for time, so we write in t equals gradient, I'll just use this 1.8. X is the square root of d. You've got to be really careful with that. A lot of people will forget the square root, and that'll stop you from getting merit. So square root of d plus c. Now we've got plus minus 0.02, so that just becomes a minus sign, minus 0.02. Okay? That's our final equation for this work. We still need to we would do a conclusion stating this equation and a discussion, and in the discussion we might identify things like control variables. We would talk about why we started our range at 0.1, why our lowest value for D was 0.1, why our highest value for D was 1.0. We might talk about any way this formula relates to physics theory. There's a whole range of things that we could talk about in terms of experimental technique, how we can ensure we get the most accurate or precise results possible, and what this experiment means. One good thing to do is to consider what using that formula to work out the time taken for perhaps a much larger value of D or a much smaller value of D, and then actually going and testing it. So if we used our equation to predict what the time would be for maybe 0.05 meters, so 5 centimeters, then using this formula we can work out what the time is. I might just do that now because it's quite an interesting little exercise. So, right, I might get it on the back here so it's easier for you to see. So our formula was t equals 1.8 square root d minus 0.02. So if d equals 0.05 meters, then the square root of d would be this value, and we can times that by 1.8. So we'll be doing t equals 1.8 times the square root of 0.05 minus 0.02. Minus 0.02. Okay, and that comes out as being t equals 0.38 seconds. All right, so we could go back to our RAM and test that using a stopwatch and see how well our formula supports the reality. So if when we're timing it, we did get close to 0.38 seconds, maybe 0.4 as a good ballpark figure, then that suggests that our formula is quite reliable, particularly for lower values of D. All right, well done guys. Let me know if you need any extra help or support with that.